Thanks for watching the presentation for our paper, Fast Quasi-harmonic Weights for Geometry Data Interpolation. I'm Yuwang from MIT. So here's a brief summary of our paper. Simply speaking, in this work, we propose a novel formulation for a geometry variational problem whose solutions can be used as a fast method for computing skinning or interpolation weights. Our method leads to orders of magnitude speedups over previous methods, allowing weight computation in near real time. For the problem setup, skinning is perhaps the simplest and most popular method for shape deformation. Given a shape with some control handles, usually in the form of skeleton, we would like to compute the skinning weight function for each bone. In these figures, we are showing some typical skinning weights. Each skinning weight function is associated to a bone, indicating its spatial influence across the domain. The weights decay smoothly when it goes far away from the bone. Traditionally, skinning weights can be drawn by artists, which is a tedious process. For the automatic skinning weights, current state-of-the-art methods solve large-scale optimization problems. While these methods give high-quality weights, the optimization requires a substantial amount of computation. For example, this Asian dragon model has more than 1 million tetrahedra. Previous methods can take hours on this model. Our method, in contrast, takes less than a minute, with potential for further speedups. That's a brief overview of our method. So, what makes it a good site of skinning weights? As shown in previous work, some properties are desired for skinning weights. It includes the Lagrange property, which is saying that the bone's weights should be 1 at the bone and 0 at other bones. And we would like the weight functions to sum to 1 everywhere. That's the partition of unity. Non-negativity and no-local extrema properties are also necessary to avoid counterintuitive behaviors. We will have some examples later. Again, these have been established in previous work. For now, we just need to know that we have such a list of properties for our weights to satisfy. The famous bounded biharmonic weights put all these desired properties as constraints in an optimization problem, and put another important property, weight smoothness, in the objective function. So it searches the smallest weights as measured by the Laplacian energy under the constraints that all these properties hold. It has been shown that the combination of the objective and constraints leads to desired skinning weights. So these methods are referred to bounded biharmonic weights BBW and monotonic BBW, depending on whether or not the last constraint is included. Here is a list of some relevant methods to compute skinning weights. While a bounded biharmonic weights is the only method that satisfies all the desired properties we mentioned, it's much slower than some other methods in the list. Some of them only require solving a linear system, which is much faster. Next, we will talk about our method that can make it fast. So let's talk about our model. First, we introduce the notion of quasi-harmonic weights. Consider solutions to the so-called anisotropic Laplace equation. The equations are defined using the anisotropic Laplacian operator, which is the weighted sum of partial derivatives. The weighting coefficients come from a tensor field A, which is a positive definite everywhere. With model saying that between bones, the weights decay smoothly from 1 to 0. The rate of weight decay is controlled by the tensor A. As an example, I'm showing a tensor field here. That's just an example of A. It can be any positive tensor field. The tensor field is a 2x2 matrix. I'm showing its condition number as well as the first principal direction. tensor AX penalizes the weight decay along the principal direction more than to the orthogonal direction by a factor of the condition number. Given the tensor field A, we can solve the associated differential equation. Here is how the solution looks like. Indeed, it seems to be a reasonable weight function. Quasi-harmonic weights simply use the solution of the differential equation as scaling weights. We see the weights are generated by the tensor field A. Why quasi-harmonic weights is an interesting model? It can be shown that for any positive tensor field, the generated quasi-harmonic weights satisfy all the 4 desired properties. In other words, quasi-harmonic weights provide a parametric family of weights that automatically satisfy all these desired properties, which is nice. In addition, the family of quasi-harmonic weights is also suitably rich. What I mean is that we can actually show that for any prescribed weight function W, under suitable conditions, there exists a tensor field A generating it. That is, the weight function W is a solution to the associated differential equation. Thus, we can search for the optimal weights only within the family of quasi-harmonic weights. Such restriction, restricting the weights within a smaller function space, does not limit the representation capacity of the weights. I will not talk about the theory in detail. If you're interested, you can refer to our paper for careful analysis. Basically, it's closely related to a problem in optimal control, an inverse problem, the so-called problem of distributed parameter identification. There are many theoretical results due to applied mathematicians. The key point is that it is theoretically justified to restrict the weight candidate to quasi-harmonic weights only. After explaining our model of quasi-harmonic weights, here comes our method. We simply search for smooth weights within the family of quasi-harmonic weights. That means the weights are generated by some tensor A. By translating it into the mathematical equations, here is the optimization problem we arrive at. We have a variational problem with PDE valued constraints. It may look complicated at the first glance. However, due to 2 simple facts, the problem can be transformed into an unconstrained optimization problem over tensor field A only. We apply a standard finite element method to discretize this problem. After discretization, we have all these matrix valued variables and constants. I'm not going to go through its definitions carefully, but the point is the weights are uniquely determined by the tensor matrix by solving a sparse linear system assembled by A. The gradient of W with respect to tensor A can be derived easily. In the paper, we showed that it involves solving the same linear system one more time. Once we can evaluate the gradient, theoretically, any gradient-based optimizer can be used. However, straightforward solutions can take too many iterations. We propose a simple solution for this problem. The first thing one may try is LBFGS, which does not work well for this problem. It can take hundreds of iterations, as shown in the blue curve. We found that Adam solver, despite not a typical choice in geometry processing, works pretty well for our problem. It converges much faster. But it still has a long tail of convergence as shown in the red curve. We propose a customization to the Adam solver by resetting the accumulated momentum term to 0 in every few iterations. This removes the long tail and it converges quickly. For most models, our method converges in 10 to 20 iterations. That being said, our method requires inverting 10 to 20 linear systems that share the same sparsity pattern. Here's another observation for further speed up. By analyzing the time that different phases take in solving a linear system, we found that symbolic factorization dominates. so we do symbolic factorization once and reuse it. This effectively makes the linear system solve 10 times faster. There are a few other minor details I just want to briefly mention. We need the tensor field to be positive. We can directly parameterize its Cholesky factor to do that. When applying gradient descent, we can backpropagate gradient to the Cholesky factor. Also, discrete weights W can be mildly negative due to violations of the discrete maximum principle. For fire comparison to previous methods, to avoid negative weights, we introduce a small modification to our method. We project the weights back onto the probability simplex. The projection is differentiable and it only adds small extra cost. This is a minor change and there are other possibilities. We have discussed all the ingredients of our method, and let's look at some results. The major advantage of our method is speed. As shown in the table, we are 2 to 3 orders of magnitude faster than previous methods. Regarding the quality of weights, the weight smoothness is our ultimate criteria for weight quality. From the table, we can see that our weights have a similar smoothness energy compared to previous methods, while being much faster. Here we visualize our weights as color blending. Our method generates visually similar weights to previous method. A different example. And another example. It's not very informative as the weights are quite similar. As a validation, indeed our weights are free from local extrema. Our weights are more similar to the monotonic bounded by harmonic weights than the regular one, when the monotonicity constraints become active. As I mentioned at the beginning, a weight monotonicity is really an important property. The BBW weights of this Barnes arm are not exactly one as a hand, so transforming the shoulder affects the hand, leading to noticeable artifacts. This is not the case for monotonic BBW and also for our weights. Here's another example. The weights are used to blend colors on the domain. BBW without monotonicity has a local extremer at the hand, has a local extreme at the tail, which is not the case for our method. In summary, our formulation is theoretically justified, transforming the problem into an unconstrained one. Combined with an efficient optimizer and numerical solver, our method is much faster compared to previous methods, allowing weight computation in near real time. Fast weight computation opens many opportunities for future work, such as the joint optimization of control handle placements as well as the weights. While our method is designed for a concrete problem of variational weight computing, this approach potentially can be used to a large range of applications. Our method can be viewed as searching for the optimal surface metric or geometry operator under certain loss function or energies. Similar techniques may be applied to geometry deep learning or computational design. That's all. Thank you for watching.